Hi,
Yep.
everybody. Thank you for being here for OTTER today. We have Jonathan Taylor, and he's going to talk to us. He's going to give us a beginner adventure into the world of groupoids and their C-star algebras. So take it away.
Thanks very much. Thank you, Meredith, for the introduction, and thank you to the organizers of OTTER for inviting me to talk. I just wanted to give a pretty chilled and relaxed kind of introduction to things. There's not going to be a huge amount of technical, like you need to know exactly how all this works because it's all going to be on an exam kind of. It's not like that kind of talk. It's very kind of basic introduction and step into the shallow, like a foot in the shallow end of the pool of these objects. Yeah, so like the kind of motivation, well, the first question I want to ask is, what is a groupoid? So if you picture like you have these objects called groups, which are, you know, your sets with some invertible associative operation on them. And then on the other end, you might have spaces, which is kind of vaguely worded as just spaces. So think sets or topological spaces or these kinds of things. If you were to put these two categories of objects onto a spectrum, what would the middle kind of look like? And that's the kind of question that groupoids looks to answer. So groupoids encompass the spectrum of objects that go between groups and spaces. So they are like groups in that they have a multiplication, but this multiplication is only partially defined, which is why they're not like groups. They're like, say, topological spaces, but they have a little more structure to them. You have some built-in dynamics. They're like topological spaces with a dynamical system built into them. And you could like talk about, oh yeah, groups, you can talk about topological spaces, but the most interesting groupoids are the ones that are kind of a mix between the two, that are half group and half space-like objects. So there are a couple of different equivalent ways to define a groupoid, and the definition I've taken is from a lecture series, well, some notes written by Aidan Sims accompanying a lecture series back in 2017, and this is the definition that looks most similar to what the definition of a groupoid is. So, before I get into this definition, if anyone has any questions at any point, just feel free to interrupt me. I would love to answer questions. If you have some, like, I would rather talk about something that people are interested in than just ramble on and have people get bored, possibly. So, a groupoid is a set together with a distinguished subset of the product, which we call G2. So this subset is going to be our composable pairs. So these are the objects that we can actually multiply. And then you say, okay, well, what's multiplication? It's a map from these composable pairs back into the group, where you say, okay, I'm going to take a pair that's gamma and eta, and I'm going to multiply them to gamma eta. We also want to have an inverse map, which we'll just call gamma maps to gamma inverse from G to itself. And this collection of objects should satisfy the following three axioms. First one is that the inverse of the inverse of an element should be itself. So you don't have, well, this one is, if you've done any group theory, you'll know, okay, yep, this makes sense. It isn't exactly the definition, but it follows immediately. If you have two composable pairs, so gamma and eta, then eta with zeta, then you should be able to compose the triple. So gamma eta should be composable with zeta, and then gamma should be composable with eta zeta, and these should agree. These compositions should agree. And this is an associativity condition. If you look at just this last bit, it says, yep, I've got associativity. We need all this stuff about the bits beforehand, so that because the multiplication is only partially defined. And if it's only partially defined, you have to say, well, if we have two pairs that we can compose like this, so like two arrows, if you like, then you should be able to go along both arrows and get to the end. Then if you have an element paired with its inverse, this should always be composable. And then when you do compose an element with its inverse, it should act as an identity. So if I have this element gamma and I compose it with its inverse and then I multiply another element eta by this, I should just get eta back. And if I do the same with eta, I should just get gamma back. So if I multiply by inverse and the original object on the left, I should get eta back, and vice versa. So then this is one of the definitions of groupoids. Another common one that you get is to just say that a groupoid is a small category with inverses. If you know what a category is, or you already know what a groupoid is, then this is a perfectly valid definition. However, it's a definition that you often see in talks when someone doesn't actually want to go into the details of what makes a groupoid, and they want to say, oh, I've defined a groupoid. So I find this definition not particularly useful other than to write it down quickly. I prefer writing things a bit more concretely. So groupoids are like groups in that you have an identity element, but unlike groups, you may have more than one. And the reason for this is if you have two elements in your group that are not composable, or in your groupoid that are not composable because your multiplication is only partially defined, then the inverse, or each of those elements multiplied by their inverses may be two objects that act like identities, but you can't multiply them together. So you can't do this usual proof for groups that you get a kind of unique inverse. You no longer have unique inverses, which of course leads to a bunch of fun stuff. And there are a couple of distinguished subsets of the group or the groupoid that we are interested in, or that are useful to have notation for. So firstly, for any element of the group, which we sometimes call an arrow, you can define the source of this gamma as its inverse multiplied by it. So this is kind of like where gamma starts, if you like. And then you can define the range of this as gamma times its inverse. And the reason we call this the source and range is if you picture that gamma is some kind of like invertible, if it's a bijection between two sets, the source of gamma, this gives you the identity on the domain of the bijection you have, and then the range of gamma gives you the identity on the codomain. So you can think of the source and range in that way. Then we say that the unit space of this group is the set of all sources of elements. And another way of, like, this is one way of writing it. Another way is to say the range of all elements, because I could just replace gamma by gamma inverse in each of these constructions and I would swap the range and source around. Or I could say the set of all units, like the set of all identities. And it's called the unit space because it is a space of units. So whenever you multiply something by an element of the unit space, you've done nothing. It's the multiplication by one thing. Then for any unit, so this unit X, you can say, okay, well, what is the set of elements that have source equal to X? What are the set of arrows in the groupoid that start at X? And this is denoted by G subscript X. This is called the source fiber. You can do the same with the range. With a G superscript X, you get the range fiber, and then you can look at the intersection of the two. The intersection of these two things are elements of the groupoid that start and end at this particular spot, which means that you can, in particular, compose them with themselves, or with each other, and you actually get a group over this point, which we call the isotropic group at X. Another way to write these source and range fibers, and the reason I call them fibers is you could say, oh, the pre-image, you can write this as the pre-image of X under the source map, and the pre-image of R or your pre-image of X under the range map. So that's why these are sometimes called fibers and bundles. Then if you have an element of the groupoid, and like I mentioned before, these kind of identities act identically on the element you start with. So the range of gamma multiplied by gamma gives you gamma back, and so does gamma times its own source. And another kind of suggestive reason for why we call these the source and range of elements is you can show that if a pair of elements in the groupoid is composable, if and only if the source of one is the range of the other. So much in the same way you would have maps between different sets or arrows between different objects in a graph or in a category, you can only compose these arrows if where one ends, the other one begins, because otherwise they're disconnected and you can't get from one to the other. Now the next thing, we want to make it topological. So I mentioned topology before. So I like making things topological. I think that's a pretty cool thing to do. So we say that a topological groupoid is a groupoid with a topology. Who would have thought? But we want a little bit more than that. So we say, okay, well, we want the inverse map to be continuous. And because the inverse map is its own inverse, well, the inverse map applied to itself gives you back the identity. This will be a homeomorphism. And you also want the multiplication to be continuous. And the topology with which the multiplication should be continuous is the subspace topology of the product topology on G with itself. Because we mentioned before that this space of composable pairs was a subset of the product. So you just put the product topology on the big one, and then you take the subspace topology of that. Another, not necessarily like every groupoid has this. In fact, not very many groupoids have this. A condition is called étale. So we say a groupoid is étale if the source and range maps are local homeomorphisms. And in particular, in an étale groupoid, the fibers over the source and range maps will be discrete in the subspace topology. So what this étale kind of comes down to, or what this translates to in the group case would be if you had a discrete group. In the kind of topological like space case, every topological space is étale in this sense, because if you don't have any dynamics, if you don't have any like extra algebraic structure, but on the group side of things, this is exactly discreteness. And today we're just going to consider étale groupoids because they change a lot of integrals into sums, and I don't know about other people here, but I don't like doing integrals. We're also going to ask that our groupoids are locally compact, Hausdorff, second countable, because this is one seminar and not an entire course. There are people doing work on locally compact, locally Hausdorff groupoids. There are people looking into non-second countable groupoids. I don't think anyone's looking at non-locally compact ones. I think everyone has locally compact and at least locally Hausdorff as well. So it's a fun wide world out there of groupoids. So next, I mentioned earlier that we wanted a C-star algebra structure. Well, we said like the title of the talk includes the word C-star algebra. So I'm going to mention briefly what a C-star algebra is, because I didn't actually put that in this talk because I work with them so often that I forgot that there are people out there who don't. So what I'll briefly mention is that a C-star algebra is a complex star algebra with a norm, and it should be complete in this norm, so it would be a Banach star algebra in this sense. And then there is one last condition which turns it into a C-star algebra, and that is to say that it's a condition on the norm. You can recover the norm of a C-star, you can recover the norm of an element by looking at that element multiplied by its adjoint. But I can talk about that more if people are interested, but otherwise it shouldn't come up later in the talk, so we should be okay. Oh yeah, we want a convolution algebra, so vive la convolution. So we start with our locally compact Hausdorff second countable étale groupoid, which some people just call this a nice groupoid. And we look at the set of compactly supported functions from the groupoid into the complex numbers. We call this CCG. The two elements in CCG, we can define their convolution by saying f star g at gamma is summing over the elements of the source fiber over the range of gamma and writing this thing. If you've seen integral convolution formulae, then you kind of recognize this as, actually, is it on this previous one? No, it's not. You can recognize this as if I put an integral here and then a dx or a d eta here, then this would look kind of like that. And this is exactly summing over the pairs or eta xi such that eta times xi is equal to gamma. So xi here is this eta gamma, and then eta here is this eta inverse. If G is discrete, so like we just completely forget the topology on it and we just say, okay, every set is open, no one cares, then your point mass functions are continuous and span this set of compactly supported functions, because it becomes the set of finitely supported functions. And so if delta gamma is your point mass at an element gamma, this multiplication is the unique multiplication that says delta gamma times delta eta is delta gamma eta. So you can kind of embed the dynamics of the groupoid into the algebra. And then if that is only if this pair is composable. If this pair isn't composable, then this product becomes 0. We also need a star, because part of being a C-star algebra is having this involution. And the one we define is the same as the group C-star algebra, if you're familiar with this. And you say f star at gamma is going to be the function that what happens when you invert the element in here and then take a complex conjugate outside. So this is the standard construction for one of these star structures on a, when you have like functions into the complex numbers, this is usually the star you get. So now we just need a norm. So we've got a star algebra structure, we just need a norm so that we can actually turn this into a C-star algebra. And you can ask like, okay, is there a biggest C-star norm on CCG? That is a biggest norm on this vector space that satisfies this C-star property that I mentioned before. This exists. Can I remember the exact? There's a theorem called, I think, Renault's disintegration theorem, which is the funnest sounding theorem I've ever heard in my life, which I think shows you this in the group case. In the groupoid case, you do a similar thing, but you have to keep track of all the different identities that you have. But the upshot is this exists. And so then you get, and it's bounded. In particular, it's a finite norm. So you can complete this, these compactly supported functions into the full groupoid C-star algebra, which we denote by C star G. There's also a reduced C-star norm. So the way we get this reduced one is we define a bunch of like very concrete representations. And we say, okay, well, for each element of the unit space, I'm going to look at the little L2 functions on the source fiber of at X. And remember, since our groupoid is a tuple, this is a discrete set. So we just look at little L2 functions here. And we say, okay, a function on the groupoid, it's going to act on the point mass at gamma by summing over all the things that I can multiply gamma by, essentially, to get this alpha gamma here. And then I evaluate f at this alpha. This will be a finite sum because f was compactly supported to begin with. So in particular, on this discrete set, it has finitely many values because each of these discrete elements is disjoint in the greater space. And then we say, okay, well, if we take the direct sum over all these representations over all possible units, then we get a big-ish representation. And this representation will be faithful. It will be injective because if we have an element that is non-zero on some, if f is non-zero at some gamma, then I can look at the range, the range element of gamma, take the representation corresponding to that, multiply this by gamma inverse, evaluate that at the source of gamma, and I get f of gamma again. This is a kind of back of the envelope calculation I had to do beforehand to just make sure that this is the right thing, but just if you could trust me to say, okay, this is equal to this, or you could not trust me, in which case I invite you to do it yourself. But in any case, if f is non-zero at this gamma, then this representation is non-zero. So the only element that pi maps to 0 is 0 itself. So it's injective as a linear map. So then you say, okay, we'll define a norm on this compactly supported functions on the group by saying, if I have I'm just going to take the one I get from applying this representation. And this representation has a norm in this direct sum of bounded operators on this Hilbert space. And this norm exists because I didn't mention this before, but some major examples of C-star algebras, one of the big ones, in fact, probably the biggest one, is the bounded operators on a Hilbert space. This is always a C-star algebra with the operator norm. And in fact, every C-star algebra is isomorphic to some closed star subalgebra of this. That's a very non-trivial result. So if you are skeptical of that, that's entirely fair. But in any case, this object has a norm, and we say that the reduced groupoid C-star algebra is going to be this space completed in this reduced norm. This will be smaller than this full groupoid C-star algebra norm, simply because we defined the full norm as the largest one. You can take the supremum over all possible norms on this algebra, and then all possible C-star norms over this algebra, and you get something that is obviously going to be at least bigger than this. So then I want to bring this back and say, how does this compare to groups and spaces? And like, do groupoid C-star algebras really generalize group C-star algebras and some spatial C-star algebras? And say, okay, well, if G is a group, then I only have one unit fiber, or only have one unit, and the entire groupoid is a fiber, or is an isotropy bundle, a group over this one fiber, or over this one point. And so what I get are the respective full and reduced groupoid or group C-star algebras. The full one is because I've just got a group in here, and this condition up here doesn't actually mention anything about the difference between groups and groupoids. And then the second, the reduced groupoid C-star algebra, I get because when I defined these representations on each unit, if you just have one unit, this representation is exactly the canonical left representation of a group on its L2 space. So this, and then this completion is by definition the reduced group C-star algebra. So if G is a group, then this construction generalizes the construction for groups. Cool, it's very cool. If G is just some locally compact second countable Hausdorff space, and in which case we can just view, if we forget the dynamics, one way we can forget the dynamics on, or forget the multiplication, is just by saying there are no multipliable pairs, none, except you can multiply an element with itself, in which case you get that thing back. Just everything is a unit. In which case, what you get is that this full and reduced groupoid C-star algebras agree, and these are equal to just the continuous functions on the unit space, which vanish at topological infinity. And then this is a C-star algebra under the supremum norm for functions on here. And the Gelfand-Neymark theorem tells you that every commutative C-star algebra is one of these, up to isomorphism. So in fact, every commutative C-star algebra is a groupoid C-star algebra, which pretty cool. So then the interesting stuff happens when you have groupoids that aren't quite groups and aren't quite just spaces. So what happens here? So hopefully this is a motivating example. I'm going to construct a groupoid which is just going to be pairs of natural numbers. And I will denote this pair of ij as eij. And then ij will be elements of the naturals. And then the multiplication is going to be eij times ejk is equal to eik. And then they're only composable if the second number in this subscript is equal to the first number in this subscript. And then the inverses are going to be eij, or the inverse of eij will just be if I swap things around. So this will give you your, this will satisfy the relations of a groupoid that I mentioned out before. And then I'll just give this the discrete topology. You might notice that these look a lot like matrix units. So then G is discrete, so the compactly supported functions are just finite linear combinations of point masses at each eij, and I'll call these delta ij. And then the multiplication you get is delta ij times delta kl is exactly delta il if j equals k, or 0 otherwise. I put a full stop and a comma here. That needs to be fixed when I upload these lines. Anyway, and these act like matrix units, and you can take linear combinations of these. What's more, you get exactly an isomorphism between the reduced groupoid C-star algebra and the compact operators on the Hilbert space L2n. And the map that you get is you map one of these point masses to the canonical matrix unit in here, which maps the jth coordinate to the ith coordinate in L2n. You also don't need to take all of n to make this work. If I just took the set of natural numbers 1, 2, 3, 4, 5, 6 up to n, what I would get is the n by n matrices, the n by n complex matrices. So this construction really gives you like all kinds of algebras. You've got commutative ones, you've got group C-star algebras, you've got these compact operators on a Hilbert space. Yeah. And in fact, there's another example. This is a fairly heavy result due to Renault in 2008. This was Jean Renault. And he said that if you have a pair of C-star algebras that satisfy some nice properties, and so these properties are, so A is contained in B, so A and B as two C-star algebras. If A contains an approximate unit for B, so that it's to say if they're unital, then the unit of A is equal to the unit of B. That's what this means. Approximate unit is here because sometimes C-star algebras aren't unital, in which case you need to still talk about how this, like one C-star algebra can be non-degenerately included in another. If you're not familiar with this, then just picture these as unital and their units are the same. Then you also should have that elements of B that conjugate A to itself. So n star times elements of A times n will land back in A, and so will elements of, or n times A times n star. These should land back in A. And if you have elements of this form in B, these should span a dense subalgebra of B. This is called regularity. Basically, this condition says that all of the information of B is contained in the elements of B that actually do dynamics on A. So this is a kind of like way of performing dynamics on A. And then anything that doesn't do dynamics on A directly is built as a sum of things that do dynamics on A anyway. Third condition is that A should be a maximal commutative subalgebra of B. So it's just the biggest commutative subalgebra in B that contains A. And then the fourth thing is there should be a faithful conditional expectation from B down to A. If you don't know what this is, you can picture like a projection of B down to, like a projection onto the subspace of A, if you like. It is a slightly more restrictive than that. There are a couple of really nice properties that these kinds of maps have. It's positive or completely positive. Sorry. Yeah, it's a completely positive contractive linear mapping. There's a couple of other things in there that you want, this faithfulness condition, etc. But just if you don't know what this is from the get-go, just picture I'm projecting onto a subspace and this subspace is A. So the theorem of Renault says that every Cartan pair is isomorphic to a pair given by the inclusion of the continuous functions of the unit space on a groupoid into a special kind of groupoid C-star algebra. And this is, I've got an extra term in here, I've got this sigma, and sigma is going to be a twist over an étale plus other conditions groupoid. If you don't know what this is, also don't worry. It's like a bundle, it's like a complex line bundle over the groupoid, and you can still build a C-star algebra out of this. But for a lot of these conditions, this sigma part actually disappears. It's completely trivial, and you just get the reduced groupoid C-star algebra. So this by itself, you might say, okay, yeah, you've got these weird abstract pairs of, or Cartan pairs of C-star algebras. Who cares about those? It turns out a lot of people do, because Xin Li showed in 2018, I believe, that every what's called classifiable C-star algebra has a Cartan subalgebra. The classifiable C-star algebras are a large, possibly actually, depending on your idea of size, they're either a very large class or a very small class of C-star algebras. And they are the kind of building blocks of most separable C-star algebras. So they have to be simple, unital, nuclear, and a couple of other conditions, but there are a load of them, and a lot of people are very interested in what are called classifiable C-star algebras. And this result of Xin Li says that every one of these has a Cartan subalgebra, in which case And what we mean by this is that it forms part of a Cartan pair. And funnily enough, this paper is called Every Classifiable Simple C-star Algebra Has a Cartan Subalgebra, which I think is a pretty good name for this paper. But in particular, if every classifiable C-star algebra is part of a Cartan pair, and then it says that every Cartan pair looks like a twisted groupoid C-star algebra inclusion, then every classifiable C-star algebra is isomorphic to a twisted groupoid C-star algebra. So this really motivates us to kind of study, why would we look at groupoids? Why do we want to look at groupoids and their C-star algebras? Well, the answer is because they basically make up all C-star algebras. And these come up in all kinds of places in practice, and even in dreaded applications of maths, even in like physics and stuff. I wouldn't know anything about that though, because I've been in theoretical land for most of my career. But anyway, yeah, there are some references, and that was the talk. So thank you very much.